divides, where roots, where both sides, base 10, take a log, 10, take the arcane, baby, A, operations, they might be crazy.
Hey guys, my name's Summer, and today I'll be introducing the Mandelbrot Set. So is this what it looks like? And we'll be talking about this beautiful object across the course of the video. Before we begin, first we need to learn some prerequisites. What is a prerequisite? A prerequisite is something you need to understand a larger concept. Okay, what are the prerequisites we will be learning in this video? In this video we'll be learning imaginary numbers, complex plane, functions, which is my favorite, and iteration. And today, the first one, the imaginary number. Okay, the imaginary number is I squared equals -1. We mathematicians created this number to help us with our problem of not being able to do the square root of negative numbers. This is really helpful because it helps us to create this whole big number system, which we'll talk about more later. I'd like to say one more thing about the imaginary number. I think it's terribly named. It's not imaginary. Imaginary means that it doesn't exist or that's not important. For one, it exists, and it's definitely important. Like I said, it created all this beautiful mathematics. Okay, what's next? The complex numbers. Okay, the complex numbers are numbers of the form a plus bi. There's a real part and imaginary part. A is the real part, b is the imaginary part. But I'd like to be clear that a and b are both real numbers. Just because b is in the term of bi, we refer to it as the imaginary part. Now let's take an example. Okay, x squared plus 16 equals 0. Okay, and let's keep in mind that in this example, x is in the real numbers. Okay, now let's get the x's by themselves. Okay. Oh no, we have a problem here. Because we can't do the square root of negative numbers. We know that. That is because when you multiply two positive numbers together, you get a positive. When you multiply two negative numbers together, you get a positive. So, by definition, we can't do the square root of negative numbers, which means, therefore, there's no answers for x, which we mathematicians like to call null set. But now, what would happen if x is in the complex numbers? This is the symbol we use for it. Okay, what would happen if x is in the complex numbers? So, yeah. So let's get the x's by themselves again. Yay! Here we can do the square root of negative numbers because I squared is -1. So now we're going to expand -16 so we can square root it. So we can do square root it. Okay. So x squared equals So -16 times -1. No, sorry, just 16 times -1. Forgive me. Now we're gonna do the square root of both sides. Okay. So x equals. So the square root of 16 is 4. It's positive or -4. That's very important. That's a very important detail. And what's the square root of -1? I. Okay. So not only in the complex numbers did it give us one answer that's valid for this equation, it gave us two answers that work for this equation. Okay, what's next? 3, the complex plane. Okay, so for the complex plane, I'd first like to start by saying something very important. So the complex plane is like the Cartesian plane for the complex numbers. So I think that's really important. And we have the x-axis and the y-axis in the Cartesian plane, but in this case we have the imaginary axis and the real axis. So I'd first like to point that out. Yeah. So now, when we label A and B from our a plus bi, and we put the point that connects them, that's how we represent a plus bi. So that's like the geometric representation for a plus bi. Now, I'll just say one quick thing. It's not important for now, but it will be later. When you go from the origin to that point, to the point that represents a plus bi, that is called a vector, and that will be more important later. Yeah. So, now let's show an example. Okay, here, our example. Z equals -2 plus 4i. We graph -2, we do -2 plus 4i. Point that connects them, that's the point. That's the point that represents negative 2 plus 4i. Here's the vector. And first, you couldn't tell this is a array. I have 2 quick more things to say, and then I leave. So we mathematicians like to call the complex plane the argand diagram. And I'd also like to say one more quick thing, that in my opinion, the complex plane is like a really fun hotel for cool things like the Mandelbrot Set. So. Okay, what's next? 4, functions. I think that's my favorite. Okay, so I'd like to give you a quick definition of what a function is. So you take a little something, then you put it in the machine, and the machine does its work, and then there's a little output. Something comes out, and that we call an output. So this is called an input, this is called an output. Yeah. So now I'd like to show you an example of a function. Okay, so here we have f of z equals z squared plus 2, and I'd just like to say, if you wanted to know this in terms of this, z would be the input, z squared plus 4 would be the machine, and whatever comes out would be the output. Okay, so let's try it. So, f of 2. Okay, so 2 is the input. We put that in. So, the machine is doing its work by doing 2 squared plus 4, okay, blah, 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 and then we get 8. Okay, so, input 2, the machine doing its work in here, output 8. Okay, next. F of 5, let's say, equals, so 5 squared, the machine's doing its work while, the machine's doing its work, 29, so 29 is the output, and 5 is the input, so 5 input, the machine does its work, 29 output. Let's do one more example. F of 7, okay, let's try that. So x, 7 squared plus 4, the machine's doing its work in here, and then get 53. So, input, machine doing its work, output. Okay, so now I'd like to say one more important thing about my poster here. So in my poster, I'd like to specify that this is a complex function, which is what we use in the Mandelbrot Set. But yeah, so a complex function is just a normal function, but the domain and range are in the complex numbers. So I think that's it. Okay, what's next? Iteration. Okay. Okay, so iteration. The informal definition. Okay, iteration refers to repeatedly applying the same function. In other words, the outputs becomes the next inputs. Okay, so here we start here with x0, which is our seed, and then the machine does its work. We get our little output, and then this output right here becomes our next input, so we put that in. The machine does its work, we get our output. Then we put that back into our input. Then the machine does its work, output. Now, I like to say that the set of all outputs is called the order. Okay, now I'm going to show you an example of iteration. Okay, so f of z equals z minus 4 with a seed of 5, and we're going to do this 3 times. Okay, great. So, with the third, okay, so f5 equals 5 minus 4, this is the machine doing its work, and you got 1. Okay, input, machine doing its work, output. Okay, let's continue next. Now, f of 1 equals 1 minus 4, this is the machine doing its work, negative 3, this is the second iterate. Now, last iterate, okay, of negative 3, so we're doing equals negative 3 minus 4, machine doing its work, equals negative 7. This is the answer. That means that f of z, that equals z minus 4, with z to 5, in third iterate, the answer to that is negative 7. Okay, now I'd like to tell you two quick definitions. So, first I'd like to say a dynamical system is where a function describes how something changes over time, and complex dynamics is a dynamical system but using complex numbers. And complex dynamics is the branch of mathematics that you would do at university if you want to be a math major, if you want to learn about cool things like the Mandelbrot Set. Now I'll give a quick introduction to the Mandelbrot Set. The Mandelbrot Set was discovered by Benoit Mandelbrot in the 1970s. The Mandelbrot Set is based on the equation f of z equals z squared plus c, using all c's in the complex number system, starting with a c of 0. Now, this is iteration, so the machine is doing its work, giving you I, then that becomes the next input, then the machine does its work, giving you j, then that becomes the next input, and then the machine does its work, giving you k, and so on. The orbit is very important, because if you're bounded and you stay in the same range, you will be in the Mandelbrot Set. But if you don't, you will go to infinity and blow up. Now, so yeah, the orbit, if you're in the same range. If you're not, you will blow up. Okay, so now, this is why is 2 very important? Because even if you're infinitesimally over 2, you blow up. That means that if you are bounded, if you're less than or equal to 2, that's the range that you are bounded. So, if you are bounded, you're a point in the Mandelbrot Set. If you're not, you won't be. That makes clear sense, I believe. Now, this is the point where we want to come to. Okay, so the Mandelbrot Set is a beautiful fractal image made up by all of this coming together, making this beautiful image that is really beautiful. Now let's look at some examples of C to see if these 2 numbers here are in the Mandelbrot Set. Okay, let's start with C equals a half. So, f of z equals z squared plus a half. Okay, that's correct now. F of 0 equals a half, because 0 squared is 0, yeah. So now let's continue one more. F of a half equals a quarter plus a half, which equals 3/4. Now let's look at another one. So f of 3/4 equals 3/4 squared, which is 9/16, plus a half, which equals 17/16. Okay, from here we see that this will blow up because now this is greater than 1. We see that the more times I repeat this, the greater this will get. So if you think about it, the next time you do this, so 1 squared is 1, so a little bit over 1. Then you're going to be adding a half, so 1 and a half. And then you see that this will get really, so this will blow up eventually, like a bomb. Like a bomb, like this. Now we're going to see its zeros in the Mandelbrot Set. Okay, so f of z squared plus 0. So since this is basically just z squared, we're just going to take away that plus 0. So z squared. Okay, so now f of 0 equals, 0 squared is 0. So now, well, we got the same, so our input became our output. So that means the more we repeat this, the more we see this will not blow up like a bomb. This will not blow up, which means that 0 is an element of the Mandelbrot Set. In my previous examples, I was using the real numbers for C because the calculations are easier. But we got to keep in mind that the Mandelbrot Set deals with complex numbers. So in this poster, I'll be explaining what it means to be greater than 2 for the complex numbers. So let's get to it. The example that I will be using today is C equals 1 plus I. First, since we know that our equation is f of c equals z squared plus c. So I'm going to do the step of f of z. F of z equals z squared plus 1 plus I. Okay. So now f of 0 equals 1 plus I. That is because 0 squared is 0. So now I'm going to show what that means geometrically to see if that on its own is greater than 2. But first I need to explain what it means to be for a complex number to be greater a complex number to be greater than 2 for complex numbers. Yeah. And that means that the distance from the origin point to the point that we use to represent 1 plus I, or whatever complex number you're using, to see if the length of that is greater than 2, or in other words, you could say that the length of the vector, if the length of the vector is greater than 2. So let's see this example. We're going to take our I1, point that connects them. So this point is how we represent the complex number 1 plus I. And now I want to show, so we put that point. Now I want to draw the vector from the origin point to that point. And now I'm going to make our little triangle so we can use the Pythagorean theorem to see if the length of this vertex of this vector is greater than 2. Okay, let's see. So the length of here is 1 and the length of here is 1. So 1 squared equals when you put that together, it's 2, but we gotta keep in mind that it says a squared plus b squared equals c squared, so that means that the thing is square root of 2. So here we have square root of 2. Okay, so is the square root of 2 greater than 2? No. So let's continue. Next step. F of 1 plus I. So this is a little harder. This stuff is a little harder. Here's where it gets harder. So yeah, let's continue. So f of 1 plus I equals 1 plus I squared plus 1 plus I. Okay, so what is that? That is like any normal multiplication, just expand. So 1 times 1, 1 plus 1 times I, or 1 times I, 2I, and then I times I, which is -1, and then plus 1 plus I, okay, all of that. Now we're going to simplify that. These ones cancel, we add up these, and then we got 1 plus 3I. So now I'm going to see 1 plus 3I is greater than 2. Okay, let's see. So we graph that, we put 1, 2, 3, 1, okay. So this is 3, this has a length of 3, this has a length of 1. So 1 squared plus 3 squared equals the square root of 10. And there we have the problem. So the square root of 10 is a little bit over 3. So that means that it is greater than 2. So since the square root of 10 is greater than 2, this will blow up. So eventually it will eventually go to infinity. And therefore, C equals 1 plus I is not in the Mandelbrot set. The moment we've been waiting for, the formal definition of the Mandelbrot set. Okay, let's get to it. So, let P sub C be a family of complex quadratic polynomials given by P sub C of Z equals Z squared plus C. Now, it's a family because there's an infinite number of C's, and it's a quadratic because the highest power it has is 2. Okay, I'm going to just call this P and C of Z, denote the nth iterate of PC of Z, P sub C of Z. Okay, now for if you don't understand this, it's kind of like, so let's try an example. If you want the 5th iterate of something that says like C is 3 or something, we'll do, so this would be P5, 3. Okay, let's continue. Then the Mandelbrot set is a subset of the complex plane given by, the Mandelbrot set is the set of all C's in the complex plane such that the limit as n goes to infinity has the magnitude of P and C of 0 is always less than or equal to 2. Okay, there are some things that you may not understand in here. I'm about to explain. Here, if you didn't understand this, is the greater iterate you get, the greater the iterate gets. This is 0 because of the seed, because the seed is 0. And yeah, so what this says is kind of like, no matter what this kind of says, if you want to see them in little formal words, a little easier words, it's like any seed that you try, the higher the iterate gets. No matter how big it gets, starting with a seed of 0, it will never get greater than 2. Now we start the geometric definition of the Mandelbrot set. The key for C to be in the Mandelbrot set is that all the elements of the orbit have to be less than or equal to 2. Okay. These lines that I've drawn here are of length 2, so that I can draw a circle with the radius of 2. circle will blow up immediately. But everything inside may or may not. There's a difference between what the white points inside and the white points outside. The white points inside the white points inside won't blow up like absolutely immediately, and the ones outside will. What I drew here is the Mandelbrot set. Everything in black is the Mandelbrot set. Everything white is not. Now let's look at some of the special geometric properties of the Mandelbrot set. First one, the intersection with the Mandelbrot set and the real axis is -2 through 1/4. Let's keep in mind that this is counting -2 and 1/4. Okay. This part right here is called the main chordoid. It looks like a heart, and in my opinion, it looks like a bean. This part right here is a circle. It doesn't have any kind of name or anything. It's just a circle with a center of -1 and a radius of 1/4. So if you think about that, that means that -1 plus 1/4. So this one right here is -3/4. That means that the intersection between the main chordoid and that circle is -3/4. Now, I think that's really cool that a simple equation helped you get this circle with such a clean number inside, with such a clean center, and such a beautiful radius. Wow, cool. That's really interesting. Now, I like to say that everything between -2 and -1.4 is in the Mandelbrot set, but our eyes can't see those points because they're so minor that we can't see them. The Mandelbrot set is a fractal. Well, you may ask yourself, well, what is a fractal? A fractal is a figure where a small part looks like the whole big thing. Now, if we take a closer look at right here, this part right here looks like the whole big Mandelbrot set. That means that the Mandelbrot set is a fractal. Now let's look at our color Mandelbrot set. This is where it gets really fun. Okay, first I'd like to make clear that everything in black is an element of the Mandelbrot set, everything in colors is not. That's a very important key. Now, so how are these colors made? Well, they're made about how many iterates it takes for them to get past 2. What do I mean by that? Let's say, okay, so this yellow one here. Let's say one takes 5 iterates to blow up. And let's try another one. Let's say like this one here takes like 1,000 iterates to blow up. Whatever, but they're not in the Mandelbrot set, that's important. Now this is, so you can decorate your own Mandelbrot set with this. You can draw it and picture it and make it your own by using colors, and you can like, if you want to use some like yellow or stuff, or if you want to use more like blue ones, or so if you can kind of make it like, so you can pick your color and say, okay, here I want a green, and that represents it takes 15 iterates for it to blow up. So you can pick your number. Down in the link below, I have a little link for you to decorate your own Mandelbrot set. So go ahead and decorate one. Thanks so much for watching my video. I hope you enjoyed, and I hope you learned some stuff. Comment me in the description below if you go to a future class, if your university class is about Mandelbrot set one day. I have some links in the description too for if you want to know about what is a fractal by MIT K-12 and how to decorate your Mandelbrot set. There's a little website I left for if you want to decorate your Mandelbrot set. I like to say this is my first video. I'm really excited, and yeah, I hope you liked it. So comment me or put a comment or tweet me if you have any ideas for future videos. Please subscribe to my channel.